Alright guys, so in this class, I'm going to introduce you to the continuous random variables. Now before I introduce you to continuous random variables, I'm going to take you through a series of simple exercises that are eventually going to lead up to continuous random variables. So let's say that you have a wheel and you have this nice red pointer here, which is constrained to move around the circle just once. In addition, it is also constrained to stop either at 90 degrees, 180 degrees, 270 or 360, but nowhere in between. It means that the discrete angular movement theta of m in this case is going to be equal to 90 degrees. So your pointer is destined to stop. It's destined to stop at an angle that is a multiple of 90 degrees. So in this case, your pointer can stop either at 90 degrees or it can stop at 180 degrees, 270 degrees or 360 degrees. And further, let's say that the probability of any of these angles is the same. So the probability that your pointer stops at one of these angles is going to be equal to 1/4. So that's the probability mass function for this particular problem. What I would like for you guys to do is draw the CDF for this particular problem. So what you can do is take a piece of paper and pencil and draw the CDF for this particular experiment. You can pause the video. Okay, so I hope you guys had the chance to draw the CDF for the previous problem. So the CDF of this problem is going to look something like this. So the PMF of the previous problem, it was non-zero for these points 90, 180, 270 and 360, and therefore the CDF is going to take a jump at these points, and specifically the amount of jump that the CDF takes is going to be equal to the probability of theta to be equal to that discontinuity. So this jump is equal to probability that theta is equal to 90 degrees, which is equal to 1/4. This jump is equal to probability that the theta is equal to 270 degrees, which is also going to be equal to 1/4. Let's further develop this problem, and let's say that now my pointer can stop at some more additional angles. Specifically, let's say that now my pointer is constrained to stop at an angle that is multiple of 45 degrees. But it is going to be less than 360 degrees. So these are the possible angles where my pointer can potentially stop. It can stop right here, which is 45 degrees. It can stop here at 90, at 135, or at 180 degrees, 270 degrees, and 360 degrees. And further, let's say that each of these angles is equally likely, then the probability that the pointer stops at one of these points is going to be 1/8. Now, let's draw the CDF for this example now. The CDF now is going to take this shape. Notice the difference from the previous one. The number of steps has increased, and the size of each step has decreased from the previous example. Specifically, the size of each step is 1/8. So as you allow the pointer to take on multiple angles, more number of angles, the size of the step is keep on decreasing. Now further, let's say that now my pointer can stop at multiples of 10 degrees. So I have 36 such possibilities, and the probability that the pointer stops at a particular angle, 10 degrees, 20 degrees, 30 or so on, is going to be 0.028. Now let's draw the CDF for this case. The CDF for this case now is going to be looking like this. There are a large number of steps now, and the size of each step has reduced quite a bit. Moving on, let's say that now I allow my pointer to stop at several possible angles between 0 to 2 pi or 0 to 360 degrees. Let's say that now my pointer can stop at 0.5 or 1 degrees or 1.5 or 2 degrees or 2.5 and so on all the way to 360. So there are going to be 720 such possibilities. So the probability that the pointer stops at a particular angle in this sample space is going to be really very small, which is equal to 0.0014. So see what's happening, you guys. As you allow your pointer to take on numerous possible angles, the probability that your pointer is going to stop at a particular place keeps on decreasing. And in fact, it keeps on going towards 0 degrees or not 0 degrees, the value 0. Now this is the case for 0.5. That's your CDF. Now carefully notice the shape of this CDF. Do you guys think it is discrete anymore? It doesn't look discrete anymore, right? So as you let theta to take on infinite values between 0 to 2 pi, the CDF is going to look more continuous and more continuous. So what happens when you keep decreasing theta of m? The probability that your pointer is going to stop at a particular angle, it gets closer to 0. Not only that, if theta of m were to take on infinitesimally small value, then theta takes on a continuum of value between 0 to 2 pi, meaning theta, your pointer can stop at infinite number of angles between 0 to 2 pi. And therefore, probability that the pointer stops at a very specific point literally becomes 0. It literally becomes 0. And what happens to the shape of your CDF? What happens to the shape of your CDF? Now it becomes continuous. So let's introduce what continuous random variables are. If your random variable x takes on a continuum of real values, then x is a continuous random variable that is going to have a continuous CDF without any discontinuities. Now, continuous random variables are strikingly different than discrete random variables. If you recall discrete random variables, they are always going to be countable in nature. For example, I do an experiment 10 times. What is the probability that I get 5 successes? So the random variable x in this case, it's countable. Either you can have 0 success, 1 success, 2 successes, 3, and so on and so forth. Let's take an example of number of students that are coming inside of a class. That's again going to be a discrete random variable because now the number of students is also countable. However, let's say that if I were to measure the time between the arrival of 2 students, time is a continuous random variable because time is not countable. Instead, time is measurable. So those entities that are measurable are usually continuous. So for example, we measure time. So that's a continuous random variable. We measure our height. Height is also a continuous random variable. I can be 5 feet 7 inches. I can be 5 feet 7.01 inches. I can be 5 feet 7.02 inches and so on and so forth. So those entities that are measurable are always continuous. Whereas those quantities that are countable entities are discrete. So that's the primary difference between a continuous random variable and a discrete random variable. Some examples of continuous random variables are as follows. For example, if you were to measure voltage across 2 points and let that be a continuous voltage between -3 volts to 3 volts, and let's say that between those 2 points, you have a 3 ohm resistor. Let's say that you have a 3 ohm resistor, then the current is going to be continuous between -1 ampere to 1 ampere. As I'm making this video at this point, I'm waiting on my package from UPS to arrive. Now the time that I have to wait, X, be the time for UPS package. It is continuous, because the probability that the package is going to arrive at this very instant is actually 0. So these are some of the examples of continuous random variables. For problem 19.1, what I would like for you guys to do is think about an example of a continuous random variable. So we will stop this lecturette right here. So this lecturette introduces you to continuous random variables, their definition, and the CDF of a continuous random variables. In my next lecturette, I'm going to solve some problems related to continuous random variables.